end stage of inflammation is literally like a nuclear detonation, where these immune cells, they build up all these poisons, and then the last stage, boom, the cell literally detonates. I wonder what would happen if we just took the old cells from really old people and we added glycine to the medium. What do you think happened? Bingo! Good as new, just like the youngest cells. There's plenty of circumstantial evidence that glyphosate may be substituting for glycine. Even if it does it to a small degree, that's all it takes really to mess things up. Why isn't it limited? Well, the answer turns out to be glycine. Very, very interesting.
The one food most people eat every day that is silently destroying their glycine balance.
Meat, not just red meat. In fact, I think chicken is worse than beef. A lot of nutrients are important. The glycine is certainly the most overlooked critical nutrient. They will actually initiate inflammation and inflammatory reaction. You gotta kill it before it kills you. They get levels up to 100 times normal, so high in fact that a few patients have actually developed blindness from it.
Finish this sentence. If everyone added glycine to their diet, we would see far less.
Far less.
Hi everyone. There is a nutrient that your body makes, but doesn't quite make enough of, and has left us with this glycine gap that may be leading to inflammation of all sorts, maybe an increased risk of heart disease, of diabetes, of psychiatric issues, of sleep issues, of just aging more rapidly. And you've probably seen our videos floating around. I hope you have anyway. Dr. Brind and I have done a number of different videos discussing all the different aspects of glycine, and we wanted to put all of that information together in one place. So this is going to be the Glycine Masterclass. You're going to learn what glycine is, why we're deficient, how deficient we are, how to know if we're deficient, symptoms of deficiency, and what the research says about its particular benefits, and most importantly, how we go about filling that glycine gap so that we can all live our healthiest, happiest lives. And we're going to do it with Dr. Brind. So Dr. Brind, say hello to everyone before we
yes, greetings. Greetings, nice to be with you again. Okay.
Dr. Brind, tell everyone, I call you the glycine expert. You hate it when I say that, but you are a glycine expert and you have a lot of credentials. So can you tell people who you are, what your education is, and why we should be listening to you?
Okay, speaking of education, that's why I don't like to be called an expert, because an expert gives the idea that you know pretty much everything about a subject. And when you think you know about it, then you're closed to learn anything new. So I'm always learning new things. But I do know a lot about glycine that I can pass on because it's very useful. I've been studying it for about 18 years now. My scientific career goes back 54 years plus. First walked into a laboratory as a life science research professional in 1972. However, I decided that I wanted to be a biochemist and a cancer researcher in 1961. And at that time I was 10 years old. But it goes back before that. I remember a free reading period when I was 5 and a half in kindergarten. I always graduated toward it was a book about frogs. You know, we had about half a dozen books for kids. And a free reading period, you could choose one. And, you know, each day, you know, a lot of kids would choose one day and one another day. And there was one book that I liked to look up. It was about frogs. It was the only book about science. It was about biology. And that's the book I picked every day. So I learned all about frogs. I learned about cricket frogs and green frogs and bullfrogs and, you know, all of that. So that's where I gravitated, you know, from as early as I can remember what I wanted to do. It's funny, I have a grandson who has the same idea. He's now 9. And that's what he wants to do. He wants to be a biologist, you know, just like Grandpa. And he was born on my birthday.
Oh, wow.
So the tradition lives on, you know. We'll keep it going. But basically, that's what I always decided I wanted to do. 20 years after I got after I decided I wanted to be a biochemist, I got my PhD in basic medical sciences with a major in biochemistry and minor specialization in immunology and physiology. Now, what's interesting about glycine, it kind of ties these things together. Why? Because everybody thinks glycine, biochemical, you know. And the trouble with being called a biochemist or a physiologist or a biologist or whatever you want to call it is that you end up pigeonholing people. And then not only do people expect you to know absolutely everything about that particular area, but they don't expect you to know anything about anything else. And if you say anything about it, that's not your lane, right? You have to stay in your lane. The world is not really like that. but human civilization kind of organizes itself that way. But in any case, what's interesting about glycine is, yes, it is a biochemical, but when we talk about biochemistry, chemistry has to do with chemical reactions, which is substances making and breaking chemical bonds so that they're changed into other substances. Those are biochemical reactions, and when you're a biochemist, that's what your study specializes in, the reactions that these things undergo. So what kind of reactions does glycine undergo with the body? What makes glycine in the first place? How does it break down into what else? What is it combined with? What is its role? Well, glycine, as it turns out, is so fundamental that it has many, many roles, which is one of the ways people find it hard to focus on the key roles that actually make it the most important nutrient in certain aspects. And it's very fundamental in so many things because it is the most fundamental organic molecule there is. In fact, I would say that glycine can be considered both organic and inorganic. Why inorganic? Well, it's made in the inorganic world too. You can find it on comets and meteors. They really have identified it positively in comets' tails and in core samples of, spacecraft that have landed on asteroids. You can find glycine. So glycine was here long before we or anything else that lived on the earth. That's how fundamental it is. It's also an amino acid. It's about as simple as you can get a compound that has the elements carbon, oxygen, hydrogen, and nitrogen. Just those and nothing else. And it's the simplest possible amino acid. Yes, like other amino acids, it is part of the building block of protein. Amino acids are basically like Lego blocks. They're like 20 different Lego blocks that every cell in the body can stitch together or knit together to make different proteins. And that's one of the 20 ones. And they say there are 9 of them that are essential and 11 out of the 20 are non-essential. And they usually consider glycine one of the non-essential ones. Mm-hmm. However, there is an emerging, I don't know how predominant it is, consensus, I would say, the more you read, that they talk about glycine more as a conditionally essential amino acid. In other words, you can make it, your body can make it from scratch. That is, when with scratch I mean simpler compounds than that. You say, well, what could be simpler than glycine? Well, carbon dioxide, ammonia, and formaldehyde are simpler than glycine, and your liver can make glycine from those 3 things. Mm-hmm. And it does it every day. It's not the main pathway for making glycine, but that's what makes glycine non-essential in the sense that your body can make it from simpler things, but it can't make enough. People say, oh, why would God create the body that it can't make enough of this? And wait a minute, there's a lot of things your body can't make. There's a lot of things that are essential. Your body doesn't make any minerals, right? Your body doesn't manufacture iron. Right. It doesn't manufacture copper or manganese or magnesium or calcium. You need to eat all of those things. All the minerals that are needed for bodily functions are essential. You have to eat them or you don't get them. So there are a lot of things that are essential, and just because your body can make it doesn't mean it necessarily makes enough. And depending on the conditions, it may make more or less of enough, depending on the demands and what else you eat. So here's another example of a nutrient which, by rights, by the same definition of what's essential and what's not essential, meaning if the body can make it from scratch or from simpler compounds, you should not call it essential. Well, how about vitamin D, right? So vitamin D, for example, is a non-essential. They consider it a steroid hormone, but it is non-essential. Your body can make it from scratch. Really? Yes. If you get enough sunlight, yeah, your body can make it because basically it's made from cholesterol. Your body can make the cholesterol from scratch, from 2 carbon units. But then it needs that magical particular wavelength of ultraviolet light to turn that basically 7-dehydrocholesterol into provitamin D, and then vitamin D, and then active vitamin D. So it's absolutely non-essential. But if, for example, you are of a population of people who migrated in the earliest stages of humanity, migrated to the far north, for example, the Eskimos or Inuits, whatever Lapps, whatever tribes these people go by, those nice brown-skinned people who live up near the Arctic Circle, they don't get any vitamin D from sunshine. They don't get the sunshine vitamin from sunshine. The only reason that human populations were able to flourish in the far north is because they eat all that wonderful fish, and the fish oil is loaded with vitamin D. Walrus blubber's got lots of vitamin D in it. So for them, vitamin D is an essential nutrient. For us, it actually isn't, if you get enough sunlight, and most people don't. So many people are deficient in vitamin D. Now, why do they say you can be deficient in vitamin D, right? People have been talking about vitamin D deficiency all the time. But you say glycine deficiency, it's non-essential. But why vitamin D? Why? Because vitamin D was thought to be essential in the first place, originally. And so it was misnamed vitamin D. It's not a vitamin. Vitamin means vital amine. It's not vital and it's not an amine. Neither one.
Yeah.
But glycine is more like a vitamin. But in any case, vitamin D was considered essential, and it's viewed that way. So, and we experienced, as a culture, like child workers in sweatshops in the early 20th century in the United States, for example, used to get rickets, a terrible disease, which turned out to be a deficiency of vitamin D, because they would work all day, like all through the winter, they would never see any sunlight, and so they did not get enough vitamin D, which you need to make bones and so forth. So everybody knows about vitamin D, but because it was mistakenly called a vitamin, we understand you can be deficient in it and so on, and you can take supplements and whatnot. Now, glycine, the difference between glycine and vitamin D is not only is it a matter of your body can make it, but it can't make enough, but it's also a bulk nutrient. The amino acids are bulk nutrients. What do I mean by a bulk nutrient as opposed to a micronutrient? A micronutrient, you need micrograms or milligrams per day to eat. So these are all essential nutrients. Amino acids, you don't need milligrams, you need grams a day, thousands of milligrams per day. It's a bulk nutrient. You get, hundreds of milligrams from a nice piece of juicy steak. You get a couple of grams of it,
What are symptoms that you might have that would let you know that you need more glycine?
Well, ordinary aches and pains usually, especially after working out, like the next day. If you have a workout and you may be tired or whatever, but the next day you feel really sore, then you might be glycine deficient. These days at my age, even though I'm not glycine deficient, if I do a lot of exercise, I still feel, I may feel a little sore the next day. But usually, especially if you're not old, even if you are old, a lot of aches and pains typically are glycine. So usually and then people say, oh, can I get it tested? Yeah, there are laboratory tests for glycine, but I'm sure they're expensive and your insurance is not going to cover it. The best way is just take a glycine supplement. It's the cheapest and easiest way to do it, and see if your aches and pains and whatnot go away. Now, I just know, even though I don't have daily aches and pains, I used to eat what I thought was a complete diet before I got into this glycine stuff. I was not a junk food junkie. I used to eat pretty well. Now I eat better even, had too much sugar, for example, and too much dairy and all of that. But if you don't have enough glycine, then when you have any kind of trauma, if you bump your head, or if you sprain your ankle, or if you have any kind of blunt injury, or if you get from a sunburn, if it has that usual course of getting inflamed and that sunburn is bothering you the next day, it's worse. Any kind of injury you get, if it's bothering you a day after more than it bothered you at the moment, that's because of inflammation. Why should it get worse before it gets better? No reason, except you're glycine deficient, most likely.
Yep. Okay, the one food most people eat every day that is silently destroying their glycine balance.
Meat, not just red meat. In fact, I think chicken is worse than beef, actually, in terms of methionine content. Muscle meats,
Yep. Okay, finish this sentence. Okay, quick thing before we dive in, because you're about to hear a lot of numbers and science in the next 2 hours, and I don't want you trying to remember it all. So I put everything, the signs you're low in glycine, exactly how many grams you need for sleep versus inflammation and blood sugar, and the easiest food and swaps to close that gap into one free PDF. It's called the Glycine Cheat Sheet, and it's linked below, so grab it now so you're not scrambling to pause the video every 5 minutes. Okay, back to Dr. Brind. If everyone added glycine to their diet, we would see far less.
Far less, well, you hear far less bitching and moaning, I guess, from pain and aches and pains.
I love that. Okay. And then glycine is the blank of modern nutrition.
Wow. I would say it's the most overlooked of the important nutrients. A lot of nutrients are important, critically important. But glycine is certainly the most overlooked the most overlooked critical nutrient. Most overlooked. I wouldn't give it a noun, I would give it an adjective. Most overlooked.
I love that. And last one, what did you eat for breakfast, and was it glycine rich?
Yeah, well, I had my glycine lemon juice.
Okay.
glycine lemonade, whatever you want to call it. That's how I have it. It was glycine rich as a food. I don't tend to eat bone broths that much, I'm eating chicken broths. I don't have them on a regular basis. Nuts, I have a lot of nuts, like, walnuts are a good source of glycine. I don't have soybeans that often, but you know that the official botanical name for the soybean plant is Glycine Max, because it has a lot of glycine in it. It does. Soybeans do. The beans are a very good source of glycine.
Yeah, can you tell us about that paper and how many grams deficient we probably are today? It was like a 2009 blend of Sevilla. Yeah.
Yeah, this is a group that's been working on glycine for a good 20 years or so in the Canary Islands, which is part of Spain. Now it's becoming famous again because they're worried about hantavirus.
Oh, yes.
Remember the ship that was docking in the Canary Islands? Now all of a sudden people are getting familiar with the Canary Islands. It's some people think it might be the epicenter of a new pandemic. Pandemic. But anyway, the Canary Islands is where Tenerife is, the city there, where this group, Melinda Havia and Patricia De Paz Lugo, a group there has been working on glycine, and they worked out the biochemistry of how much you need depending on the different biochemical reactions, and they concluded that even from a normal diet you still need about 10 grams, that we're all short of about 10 grams a day. Now a normal diet provides actually 2 or 3 grams, so using that as a ballpark number. And also my experience has borne that out, that works very well, is that the average you need about 8 grams. Glycine is about as safe a substance as you could possibly take. I don't believe that you could actually eat enough glycine to give you real toxicity.
And what is that based on?
Well, based on the fact that you can actually, curiously enough, from the urologic surgery literature, because there's a bit of surgery that's actually quite crude. It's over 100 years old. They've been doing something called a TURP, a transurethral radical or radioprostatectomy, which is like a roto-rooter that they go in through the urethra and actually roto-rooter out the prostate tissues to open up a channel for the urine to flow. It sounds like a very crude, brutal surgery, and yet they've been doing it for 100 years. They still do it. And it's tolerated very well, and men recover very quickly. Why? When they do it, and there's a lot of blood involved, of course, they irrigate the surgical site, usually with 2% glycine. Why 2% glycine? Well, it gives you the osmotic strength to make it like plasma so that it doesn't disturb the osmotic balance, the salts inside and outside the cells. But you don't want to put salt in an open wound, right? Mm-hmm. So it's not salt. It doesn't sting. But it's you're able to irrigate it without disrupting the ionic balance. And not only that, but a lot of that glycine gets in. And some of the literature you can see they get levels up to 100 times normal, so high in fact that a few patients have actually developed blindness from it, which goes away within a few hours. And for some reason, they say that it never really bothers the patients. They don't get worried about it or anything like that. And patients recover very well from this surgery. Well, they have so much glycine in them that it probably takes them a week before the glycine gets back to a normal level. So there is just no inflammation going on. And that's my hypothesis, really, as to why they still do that surgery. But it's not a hypothesis to understand this proven fact that they have gotten glycine levels up to 100 times normal, extraordinarily high. Like, for example, I think the normal range of glycine in serum or plasma is set by the companies like Quest, the diagnostic companies that do the blood test. It's set at about 150 to 350 micromolar. Not to worry about what micromolar is, those are the units, micromolar units, 150 to 350. Why? Because normal limits is not what's necessarily healthy or optimal, it's what most people have. Most people who aren't sick, what are their normal glycine levels? So that's what it is. But you're not really healthy, I don't believe, unless you're somewhere between 500 and 1,000. Now,
yes.
if you go over 1,000, and I'm talking about, these are people who went like to 10,000 up to 100,000, some of these patients whose wound site, whose surgical site was irrigated with 2% glycine, and they recovered fine. There was no damage done to them at all. So glycine is really, really, really safe. Yeah. That being said, there are some minority of people who have GI upset symptoms if they take the straight amino acid. That's like my glycine supplement. It's the free amino acid. It's not given as part of a protein. When it's given as part of a protein, that means it needs to be digested. which is the amino acids need to be, the proteins need to be chopped up into their component amino acids. It goes in more rapidly if it's the free amino acid. It's just absorbed once you eat it. Some people react to that. Their GI tract gets more motile, but it's not many. So they may have, diarrhea or more frequent, elimination kind of thing. More, what's the word? I guess it's really intestinal motility.
Yeah.
May go up.
Just accelerated.
You take it in smaller amounts, and some people very few people who are really, really sensitive to it, I say, you know what? Don't buy my glycine supplement. Go out and buy gelatin.
Yeah.
Because gelatin or collagen, gelatin really is cooked collagen. It's kind of denatured collagen, so that it's soluble. That is about 25% glycine by weight, and that requires digestion, which means it's absorbed more slowly. So there are some people who really can't take it, and some people who don't like the naturally sweet taste of glycine. Glycine has a naturally sweet taste. That's why it's called glycine. Like similar to glycemia, glycine, glycerol, glycerol, glycerin. All of these things have that prefix because it means sweet from the original Greek,
And before we go on to what your major discovery is, I want to ask you, do you think, like you said, you're not advocating for mega doses for, autoimmune diseases or anything like that, but do you think there are any populations, athletes, people with joint-related issues, the pregnant, breastfeeding, is there any population, meat eaters, people who carnivores, people who are eating a ketogenic diet, are there people who might need more or less glycine?
Sure.
Yeah.
Everybody's different. There's an overall medium. You can start there, and then see, because that's the thing. The wonderful thing about glycine is you're really not going to get too much. You're only going to feel it when you get too little.
Okay, so like meat eaters would need more because
because you clear it out. So that's one of the seminal papers that I like to talk about that was done by a group at Oxford back in 2015, 2016. It shows you a couple of things about modern science and the way it's done, which is worth noting before, because I know a lot of people in the audience out there, they love to dig up the scientific papers and read them, and not all scientific papers are alike. Not all of them are good. A lot of them are junk, and a lot of them. For example, this paper, it was published in the European Journal of Clinical Nutrition, which is the top nutrition journal in Europe. It was one of the EPIC study, the European something plasma, I don't know what it was. It's, the acronym EPIC for a study that was actually looking at people all over Europe, looking at for the incidence of cancer and all kinds of things. This group was interested in amino acids. And like I said, everybody's got their own little box that they're in. So their lane, or their box, or their lane was amino acids. They were interested very simply in the relationship between the amino acids that you take in. You take in so many grams, the different ratios of all the 20 amino acids. And then if we look at your blood, if we look at the free amino acid content of blood, does that reflect the amino acids that you took in? Very simple question. Their question was basically to see what the correlation was. And so what they found was that it was pretty much the same. Pretty much if you ate a lot of histidine, there was a lot of histidine in your blood. If you ate a lot of leucine, there was a lot of leucine in your blood. If you ate a lot of, methionine, it was different. There's a lot of methionine in the blood, but there was one big exception, and they couldn't understand it, and that is that the people who ate the most glycine, which is who? The meat eaters. Why? Because meat is very, very concentrated in protein. And so when you're a meat eater and you eat a lot of meat, you're a carnivore diet, you get more of all the amino acids than any other kind of dietary habit would provide. So the meat eaters, what they did is they looked at a population. They took 100 meat eaters, 100 fish eaters, 100 lacto-vegetarians, right? They still ate dairy and otherwise didn't eat meat, and 100 vegans, right? 4 different dietary classifications. And they looked at the amino acids in their plasma and the amino acids in their diet. And they looked at what was in there, and everything matched up except for what? Except for glycine. Why? Because the people who ate the most glycine, the meat eaters, had the least glycine in their blood. And who had the most glycine in their blood? The vegans. Mm-hmm. Well, how is that? They didn't eat the most glycine, but they ate the best ratio of glycine. And why should that be? Why should the ratios matter? The ratios matter for a particular biochemical reason. Here's where the biochemistry comes in. When you eat a lot of meat, when you eat a lot of the amino acid called methionine. Methionine is the methyl donor. It donates 1 carbon units. It's turned into SAMe. Probably heard of SAMe, S-adenosylmethionine, which is the active methyl donor. It methylates things. It puts methyl groups on neurotransmitters and hormones and toxins and all kinds of things. Anything that needs to be methylated to have a tag of a 1 carbon unit stuck on it, that's done by activated methionine. Methionine is an essential amino acid, but because it's so essential, you really can't live without it, and your body can't make it from scratch. Your body has wonderful ways of conserving it, reusing it, recycling it, regenerating it. The famous methionine cycle, which is what everybody learns who takes biochemistry, they learn about the methionine cycle, how your liver regenerates, basically recycles methionine. Methionine, when the methyl group is given up, it becomes homocysteine. The homocysteine is remethylated by a couple of different pathways. There's some redundancy there. But that's why, because methionine is so essential. But because it's so essential, and because there are therefore so many ways of recycling it, regenerating it, your body doesn't need to take in very much. You only need about 300 to 500 milligrams a day is all you need in a subsistence diet of methionine. Wait a minute, that's more like a vitamin.
Yeah.
A vitamin 500 milligrams a day doesn't sound like much of a bulk nutrient. Well, methionine you need the least of any of the amino acids. Even though it's essential, you need it, but you don't need much. But what happens when we eat all this meat, fish, and poultry? We eat all the muscle meat, and unlike our grandma did, we throw the bones in the trash instead of the soup, right? Bone broth.
Yeah.
In the old days, they never threw the bones away. The bones is where the collagen is, because the main protein in bones is collagen. And collagen is 25% glycine by weight. However, the proteins in muscle are very low in glycine. They're very high in methionine. So now we're eating a lot of methionine that we don't need. Well, your liver considers that a toxin when you have more than you need. So as much as you'd like to think of your body doing that methionine cycle and recycling all that wonderful methionine, after you eat that cheeseburger, it is busy getting rid of it as fast as it can because you have a lot more than you need. So in that hour after you eat, you're running in reverse kind of with the methionine cycle, getting rid of the excess methionine. However, in order to get rid of excess methionine, there's basically one pathway to do it biochemically, and that requires glycine. How much glycine? 2 molecules of glycine for every molecule of methionine to get rid of it when you have too much. So the more meat you eat, even though you're eating more methionine, you actually have less methionine in your blood. And the funny thing about this group from Oxford in 2016 is that they couldn't figure it out. I mean, I had figured it out before that. I was talking to people about how just this thing, I was stating basically as pretty much fact, as far as I could understand it just from the biochemistry, that meat eaters must have less glycine in their body than vegans do. And that turns out to be true. They ended up proving that in 2016, which was basically vindication for what I had been saying based on the biochemistry. Now, you might say, why didn't they figure that out? Well, it's all biochemistry, but again, things are so specialized that they just weren't, and they had all kinds of, theory expressed in the discussion section of their paper. They had speculation as to why it might be. Well, glycine is important for this and for lipids and for that, and maybe that's why, and maybe this is why, and so on and so forth. But they never actually looked at or realized or found out from what other people had discovered and published that this is really what's going on. And that's unfortunately a sad commentary on how a lot of science is done. You may know about these various disciplines called omics, proteomics, genomics, metabolomics, lipomics, all of these omics. The only omics I really like, stand-up comics. I think they're very funny. But as for...
Yeah, I like that. That's good.
Right? But that's the only kind of omics are actually, they're not sciences. You can say, oh, I'm a metabolomics expert. Well, that's fine. That means you know how to use a particular tool. It's not really a science. It's a tool of science. And it's a very useful tool. I think metabolomics is wonderful for testing hypotheses because you can generate lots and lots of data. You want to do metabolomics? Fine. You can actually take a drop of somebody's blood And in one shot with a DNA, I'm not even privy to the details of the technology, how they do it. I think it's wonderful. But they can actually measure reliably hundreds of different metabolites, or hundreds of different genes, or hundreds of different fats, or hundreds of different
Compounds in beef.
vitamin omics, if you will, all of these omics, and just from one drop of blood. And the computer will generate the numbers for how much you have of all these things. And so now they do a lot of studies based on metabolomics or lipomics. What they'll do is they'll take every metabolite or every gene product or all of these things, measure it all at once, and then try to figure out what the difference is. So in the old days, let's say you wanted to figure out a test. You wanted to see, you had an idea that maybe a certain metabolite was a good marker for diabetes risk. Let's say you had that hypothesis, and you wanted to test one or two or three metabolites that you think were implicated in it. Well, then you could write a grant and do the experiment and so on and so forth, and see if these 1, 2, or 3 things that you're measuring have anything to do with diabetes risk. So you get, let's say, 100 patients with diabetes, 100 people who don't have diabetes, who are otherwise similar age and weight and ethnicity and all that, and see what the difference was. But you couldn't measure 100 different things or 300 different metabolites. That would be what was called in the old days a fishing expedition. Now they call it data-based science, as opposed to what they call hypothesis-based science. Hypothesis-based science is what we used to call science, right? Data-based science is what we literally used to call a fishing expedition, and nobody would ever fund a fishing expedition because the odds of finding anything useful are pretty slim. But now we have these machines, these computers, which can now scrutinize millions of data points and come out with something called a heat map, where the probability of this or that being significant and so on. And now the computer says, okay, we found a significant difference between the vegans and the meat eaters in terms of the relative concentrations of methionine and glycine, but we don't know why. So now they devote half of their paper, which is the discussion section, let's try and speculate and figure out why.
Yeah.
Instead of starting with a hypothesis, we think this is what's happening and this is why. It's just, let's see what's different. Let's just get the data, and then from the data they say, this is a significant difference because the computer says they're significantly different. What does that mean? Starting from scratch, from the difference. And then, so you get a lot of metabolomics-based science. Now, some of that generates some very good data, like, for example, the Japanese group working around the same time, 2015, 2016. First author's name is Hashizumi. They were doing studies on aging, and they were interested in mitochondria and aging. What is the role of mitochondria in aging? Because everybody knows, aging mitochondria they look like sort of like aging people. They get sort of gray and bald and craggy, and everything's not working quite as well anymore. So they had this model where they looked at mitochondria, where they took actually cells from infants. Cultured cells, which you can get from like placental tissue or foreskin tissue or whatever. I think they actually use fetal tissue, which you don't need to do, but at any rate, the youngest possible tissue from people. And they grew them in tissue culture, and they looked at the mitochondria, nice, healthy, fit, young, wonderful mitochondria. They function really, really well. Then they took some tissue from old people, people my age or older. I'm 75, and I don't know how old they were, 70, 80, 90-year-olds. They took old people's mitochondria, old people's cells, and they looked at the mitochondrial function. And you look at these, see the electron micrographs of the mitochondria. They're kind of like all, craggy and discombobulated looking, and they look old and shaggy. So this was the goal until a few years ago, and it's many quarters still. The idea is that aging is really the accumulation of oxidative damage from radical oxygen species, and these are chemical fragments that are that kind of poison the metabolic system. Things like hydroxyl radicals and superoxide radicals. People may have heard of those things. It's sort of oxygen that's like superactive, more reactive than oxygen is by itself. And then what that does is it will react with things kind of willy-nilly and make them age, make them dysfunctional. It's a little like hemoglobin A1C is where you have, it's not oxidative damage, it's sugar damage. and you can tell how much was around. But in the case of this oxidative damage, that was always thought to be the case. So they said, okay, we're going to do a study using genomics. So that's what they use. They use genomics. So these are genomicists. I don't think they really followed it up. I haven't found any evidence that they followed up this most important finding. So they did a genomic analysis, and they said, what genes, if any, are upregulated or downregulated in the old person's mitochondria versus the youngest person's mitochondria. And so they, you measure all the gene products that are expressed to see what enzymes are actually, see if you can tell what enzymes are being expressed or underexpressed or overexpressed, you can tell what genes are being turned on or turned off, which means what enzymes are there active to do biochemical work, like to change one amino acid into another. And they found that there were two mitochondrial enzymes. One was called GCAT, and the genes were called GCAT, and the other one was called SHMT for serine hydroxymethyltransferase. Two enzymes, which are the little biochemical machines that turn precursors into glycine. The two major pathways of glycine synthesis in the body get switched off in old age. And they went, wow, that's amazing. All we got are these two genes are turned off. So, gee, I wonder what would happen. They went on further experimentally, and they said, I wonder what would happen if we just, since that means they're making less glycine, I wonder what would happen if we just took the cells, the old cells, from really old people, and we added glycine to the medium. And what do you think happened? Bingo! Good as new.
Wow!
Just like the youngest cells. And, and they couldn't tell why, and I still don't know why. I still would like to know exactly what's happening in the mitochondrion, and it may have to do with glutathione in the mitochondrion, I don't know, which is another very simple 3 amino acid compound tripeptide that's made from glycine and 2 other amino acids. It was just that they put, it was a reasonable, assumption, some multiple of how much glycine was there, but it was enough to restore normal function. What they, not only did they find that glycine was key, and they did not find actually why glycine was key, but what they did prove, really, and it'll be a while before the field catches up and realizes they proved it, is that aging is not an accumulation of oxidative damage. That's not what aging is. So certainly in the mitochondria, it was just glycine deficiency that was making these things age, and the reason why they were glycine deficient, that they were the genes with aging, whatever other reason it was, with aging, the genes that actually code for the enzymes that make the glycine were getting switched off. And if you just substitute with glycine, it corrected the damage. So that made me feel good. I've been taking glycine supplements for many years already.
Well, and that's...
I've been taking these supplements for 5 years, 7 years myself.
Well, yeah, and I want to get into that, but that kind of like dovetails nicely because, that Glynac supplementation, they've been doing that research and showing that they can reverse several hallmarks of aging with Glynac, glycine, and N-acetylcysteine. And Dr. Brind's hypothesis is that perhaps the glycine is more important because N-acetylcysteine is so much more readily available.
Yeah, it's hard to imagine a cysteine deficiency unless you take a lot of Tylenol. Acetaminophen, because that actually poisons your liver quite directly. It inactivates the cysteine, which is one of the 3 amino acids in glutathione, which is glycine, glutamic acid, and cysteine. Yeah. And the cysteine, which is the part that actually acts as an antioxidant, because glutathione is a very important antioxidant, and it's the cysteine part of it that gets inactivated by what's called paracetamol or acetaminophen, Tylenol, if you will. So if you take a lot of Tylenol, and there are people who take Tylenol every day because they have all kinds of aches and pains, mainly probably because they're not getting enough glycine. But if you take a lot of Tylenol, you'll be short of cysteine. And so you can get a cysteine deficiency, but you wouldn't normally do it if you have a normally omnivorous diet, because if you have a high methionine diet, it's also high in cysteine, because the sulfur-containing amino acids, those are the two, go together. But they also, cysteine is made from methionine. So it's hard to imagine outside of, basically being pharmacologically poisons by chronic use of Tylenol, that you're going to be deficient in cysteine. And what troubles me about the research, the Kumar and Sekhar's research, is it's all about GlyNac. Why didn't you try one and the other separately? Sort of the obvious experiment to run, and I haven't found evidence that they've done that. Maybe they've done it since, I don't know. I haven't seen lately any evidence that they've done that. But they also believe it has to do with the concentration of glutathione. And glutathione has been shown, if you take glutathione supplements, it's also very beneficial if you sort of megadose on glutathione supplements. But you have to remember, glutathione is every bit as good a source of glycine as collagen.
Yeah.
It's about 25% by weight. So, you can get the effects of glycine by taking glutathione, or by taking collagen, or by taking straight glycine.
Yeah, which we're going to talk about in a second, but I can't believe we've gotten this far in the discussion. Now, I kind of want to give a wrap up. So we're talking about the smallest amino acid. It has the biggest job. It's got a structural role, right? It's 25% of collagen weight, in our skin, our joints, our tendons, our gut. You were talking about that biochemical role, building block for proteins, DNA, creatine, glutathione, bile acids. But also, there is an electrochemical role, and I learned about it.
Oh, yeah, that's what I was getting to. Yeah.
Yes. So take us. What's the electrochemical role? Yeah.
The main reason it helps people, and it's that the deficiency is so destructive, has to do with its role as a bulk constituent of plasma, not even as a building block of protein. And that is because of a role that's not biochemical. See, that's where I say I have specialty in physiology, immunology, and biochemistry. So I talked about the biochemistry of glycine, how it's made and what it participates in and why you end up being deficient in it. But its role in physiology and immunology is really where it's key. So the physiology is that it has a physiological function at the surface of a cell, especially the immune cells called macrophages, which are the cells that do inflammation. Those cells, just like many other cells, they are activated by electrochemical switching systems. It's an electrochemical switch at the surface of the cell, on the cell membrane, that actually turns the cell on in really a strictly analogous way to the way a light switch on the wall will turn a light on. So you have a light switch on the wall, let's say the light is off. So there are two electrical poles on that switch. Well, one of them is connected to the electricity, right? Mm-hmm. So that's hot. And then the other one is cold unless you turn the switch on, right? So the potential, voltage is another way of saying electrical potential. It's called voltage. So the voltage between the two poles of a switch on your wall is what? Everybody knows, 120 volts. And what happens when you turn the switch on? When you turn the switch on or close the switch, close the contact, now the two poles are connected. What's the potential difference between the two poles? Zero. And what does it do? It activates the light. Now the current is flowing through the light and it's illuminating the room. The cells that do inflammation are not activated to do inflammation unless they get an electrochemical signal that actually flips the voltage at the cell surface from its resting potential to zero. Well, its resting potential is not 120 volts. It gets higher than that if you're an electric eel. But we don't get into that. That's a very specialized kind of biological situation. But just your ordinary cells, like your nervous system, the resting potential is about 0.07 volts, 70 millivolts. Small voltage, but for a cell that's critical. Now, when a macrophage is called to the scene of a crime or wherever there is damage, cell death, damaged cells are dying, there's some kind of injury or some kind of infection, the macrophages come along and they get activated to what's called an M2 stage, where what they do is they just clean up the mess. They'll, like little amoebas, they'll go around and they'll clean up the mess, and that's all they'll do, as a prelude to healing, for healing to go on. However, if there is an actual infection, they are activated to another level. And that other level, they will actually initiate inflammation and inflammatory reaction. They'll start secreting all kinds of poisons in an effort to kill whatever microbe got into you before it kills you. You got to kill it before it kills you. So that's what what the macrophages do if they are so activated. Now, in the act of being quiescent or in an M2 stage or a resting stage, just from the ordinary action of going around, acting like an amoeba and stuff like that, there's a lot of maneuvering of the cell membrane, a lot of changes. It's a very dynamic system. In that dynamic movement in the life of a cell, there's going to be a lot of leakage of ions. Some ions will leak in, some will leak out. And the importance is that there's a stable equilibrium between the inside and the outside of the cell. There's not the same concentration of each ion, but the same overall balance is there. But each ion will be different. So, for example, sodium ions are very high outside the cell in concentration, but very low inside. Potassium ions, the opposite. Chloride ions, also very high outside the cell, right? The blood plasma, sodium chloride. Well, the main salt in there, sodium ions and chloride ions. So chloride ions also high outside the cell, but inside the cell, no. Chloride ions are very low. So now you have a potential, because of the balance of sodium and potassium and chloride and the other ions, the resting potential is about minus 70 millivolts from the inside to the outside. So the inside is negatively charged relative to the outside. So if you have a little channel, little pores, they're called ion channels, that ions can diffuse through selectively without having to expend any energy, they can be allowed to leak in, then you can stabilize things. If you allow chloride, for example, to leak in, that means it maintains a more negative concentration inside the cell than outside. So it tends to keep the membrane polarized or even hyperpolarized so that it's negative, more negative than 70 millivolts inside relative to outside. Now, from all of that movement, or from, and then just from the movement of being activated to an M1, what I call the mend mode, clean up the mess mode, rather than the rend mode where they're actually secreting poisons and doing inflammation. Just from the more quiescent, activity there, the non-inflammatory mode, you will get some leakage, and that membrane potential of 70 millivolts will tend to deteriorate just from leakage. And so it's very prone to be activated, because if that deteriorates, it goes down to zero. Now you get a depolarization, a big influx of calcium, which is a major switching system, and then it switches into the M1 mode. If you have enough glycine around, that doesn't happen. Why? Because the chloride channels, which allow chloride in. Chloride is a negative ion. It's high on the outside, low on the inside. So if you have a channel that selectively allows chloride to come in, that keeps up the voltage, which keeps the switch off. But these chloride channels are actually what are called glycine-gated chloride channels, which means glycine is not acting in a biochemical way. It's not participating in any biochemical reaction. It's actually acting as like a trigger lock, as a gatekeeper, to keep those gates more open. When the glycine-gated chloride channels, also known as glycine receptors, are kept open enough chloride will naturally diffuse in to keep up that polarization, that voltage. And so you don't get activated into the inflammation mode, into the M1 mode unnecessarily. So what are the situations where it's necessarily done? Well, a lot of this work was done by a very good group working at the University of North Carolina back in the 90s, headed by Thurman, who was actually a toxicologist. He passed away, unfortunately, in 2001. I think he was only about 61 years old. Had a heart attack, which, ironically, I think if he had taken glycine supplementation like I did once I realized glycine was pretty important, I think he probably wouldn't have had a heart attack, because glycine will actually, not to get on the FDA's radar screen as making medical claims for anything, this is a nutritional function of a natural nutritional substance. Yeah. Is what I think prevents us from getting heart attacks and strokes and things like that, and generally getting cardiovascular disease, because those are now understood to be results of chronic inflammation. Well, why is the inflammation? Well, the inflammation is because of glycine deficiency, so that these macrophages now will start doing inflammation. And because that always happens in the case of injury, we think it's normal. I always thought it was normal. You sprain your ankle, it gets inflamed. You get a sunburn, you get inflammation. It gets worse before it gets better, right? Because of the inflammation that results from the initial insult. Well, it turns out the initial insult won't actually give you any of those problems unless you're glycine deficient. And what's happening, of course, is that there's enough glycine to keep those glycine-gated chloride channels of the macrophages open enough to allow enough chloride to influx into the cell. Now, just a little bit of a side here, that explains why also you need a lot more glycine than you would just need for biochemical functions. That's another thing that kind of has thrown us off the trail. It's like, oh, come on, you got 100 or 200 millimolar micromolar glycine in your serum or your plasma. Wow, that's plenty. You shouldn't need it for anything else. That should be enough to make all the protein you need, and it is. But it's not enough to keep the concentration high enough to keep those glycine receptors, those glycine-gated chloride channels open enough to allow chloride to keep those macrophages not doing inflammation when they don't need to. When do you not need to? You don't need to when it's just injury. Why would you need your immune system to start secreting poisons that only damages normal tissue if you just got injury or massive cell death? And by the way, that's also normal. I mean, there are normal things that happen physiologically that cause injury. Blood circulation, high pressure fluid system, branch points, very high pressure, especially where your coronary arteries branch off from the systemic aorta. What do you get? Turbulence. When you get turbulence, what do you get? Little micro injuries are bound to happen. If there's no inflammation there, they just get repaired, but they do get chronic inflammation because people are chronically glycine deficient.
Ovulation.
Another example. Yes, ovulation is another example of that. Ovulation is actually quite a violent process. One ovary or the other every month during your fertile years. If you're a woman, boom, it's like getting shot out of a cannon. It necessarily always damages the surface of the ovary. Well, once every other month, it heals pretty well, no problem. But if you're glycine deficient, this was another observation that was made at least maybe 40 years ago. The observation that epidemiologically that the incidence of ovarian cancer was directly proportional to the number of times in a woman's life that she is ovulated. Yeah. So if you have more kids and you start having kids earlier and you breastfeed all your kids, you ovulate fewer times, you have a lower incidence of ovarian cancer. Even birth control pills, lower incidence of ovarian cancer, because why? They inhibit ovulation. That's their main function, which is why they shouldn't really be called contraceptives. They're really anti-fertility drugs. In any case, that's what they do. They inhibit ovulation, so they're going to lower the risk of ovarian cancer. However, they increase the risk of breast cancer because they keep your blood in a system in a situation where there is lots of estrogen and progesterone all of the time, rather than just a certain part of your cycle. So that increases the growth of the breasts. And what happens during that third week of your menstrual cycle, when you've ovulated but the ovulation didn't result in a conception, and the egg sort of dies off, then so do the cells that started to grow in anticipation of fertilization. So just ordinarily, if you're a woman, I guess you know this firsthand. I could never know it firsthand, but of course in the third week of your menstrual cycle, you may feel breast swelling or tenderness, typically, and then it goes away because they're actually undergoing a mini growth spurt in anticipation that they may have to grow more to develop milk to feed a baby 9 months later. But if they don't, then those extra cells now die off. So month after month after month of menstrual cycling, you have cells dying off, and then you end up with an increased risk of breast cancer, which is also proportional to the number of times that you have a menstrual cycle. So all of these things fit the epidemiology, which is just looking at the data to see what happens as a result of different exposures. It doesn't tell you why, you just see correlations, but the epidemiological data has actually supported the data about inflammation all the way along. And how does that tie into glycine? Well, you look at glycine and the incidence of cancers, glycine and heart disease, and there have been studies that show pretty well that that glycine is actually preventive. So, for example, there was a good study done by the Cleveland Clinic in 2015 that was looking at, because it's the Cleveland Clinic, it's huge, and they have a huge database. So they were looking at genetic diseases. They had a database of patients with what's called a CPS1 deficiency. CPS is called carbamoyl phosphate synthetase, which doesn't mean much to most of your listeners, but we'll move on. Carbamoyl phosphate synthetase, CPS, is the first step in the urea cycle, right? The waste product from protein metabolism is ammonia, and then ammonia is converted into urea to make it something nice and non-toxic that can be stored in the blood in high concentration without toxicity. Urea can go very high. So what happens, though, if you have a defect, if you have one gene that's a clinker enzyme that doesn't do the incorporation of the amino group from protein into the first step in the urea cycle. It's called ornithine. Well, ornamine takes it, that the amino group most often comes from glycine, because glycine is just about the most abundant amino acid in the body. I'm not sure if it's that one or if it's glutamic acid, but it's one of the most abundant amino acids, and in fact it is the main source of urea nitrogen. What happens if you can't make urea nitrogen as well? The urea cycle backs up a little. What does it mean that it backs up? It means you get a backup in the supply of glycine. So people with that amino acid deficiency, that inborn error in urea metabolism, those people have more glycine in their blood than most people do, because glycine backs up as part of their metabolism. So they have higher levels of glycine, and then guess what? Lower incidence of what they call MACE, major adverse cardiac events, heart attacks and strokes, was what this Cleveland Clinic study found in 2015. So they have actually shown this observational study was able to find a real solid evidence that glycine concentration is key. And they figured out it was glycine because you can eliminate other variables. You know, once you adjust for the glycine concentration, you know, the difference goes away. So that it was the glycine that was higher in these patients, and it only happened in women. That's probably because only in women where they have a lower incidence of MACE, major adverse cardiac events, because they had more glycine in their system. Probably just because there are differences due to the sex hormones in kidney function, and so you can only have this error that they were looking at if you only had one bad gene, not two. Because if you had two bad genes, you'd die. You wouldn't make it through pregnancy. Because you can't make urea at all. So these people, they could make urea just less than normal. But in the males, it was probably compensated for by the masculinization of the kidneys, But in any case, in the women, they showed that it was, yes, indeed, it was the glycine deficiency, the glycine surplus caused by the deficiency of this enzyme function, CPS1, which was responsible for their lower incidence of MACE. And it was like a 12.5% decrease, and it was very, very significant. One of these P equals 0.00001.
Very high, very low.
There was no question that the glycine was responsible for it.
No.
What they didn't do is they didn't really look at the mechanism for why glycine would do that. And the mechanism, there's several mechanisms by which glycine decreases clotting, and it's hypercoagulability, or the tendency for blood to clot when there isn't any need for it to clot. That is what is the immediate cause of strokes and heart attacks, and these MACE. And what glycine does, a few things, three different things. It actually, first of all, it decreases the level of inflammation through these glycine-gated chloride channel functions on macrophages. That's number one. Number two, it because of what the increase in inflammation, the decrease in inflammation means that you're making less of these, what's called pi1. In inflammation, you have an increase in pi1, which is plasminogen activator inhibitor 1, which inhibits the unclotting. When blood clots, it clots and then it unclots sort of rapidly at the same time. It's a very highly coordinated activity. Can you imagine if you got a cut and your blood clotted, and then your whole body, all your blood clots, and then you're all clotted up and you're dead, right? Yeah. So your coagulation system, it's a cascade of enzymes that build the clot, and then there's another cascade of enzymes that's initiated at the same time that tear down all the clots inside the blood vessel, and allows the clot to persist only in the hole that is being plugged where the blood is leaking from. Brilliant system, right? Brilliant coagulation system. So what it does is it increases pi1, which means the clots tend to stay and not dissolve as quickly. So it increases coagulability of blood in that way. That does inflammation. The other thing that inflammation does, it increases the liver synthesis of, I think, factor 7, I think. One of the clotting factors gets an increase. So it increases the clotting part of the cascade. It it decreases the unclotting part of the cascade, and then to boot, the platelets themselves have glycine receptors on them. So now with more glycine, they are less sticky, less likely to be stuck together and to form a plug and to cause coagulation. So it's inflammation, which increases pi1, decreases the formation of factor 7, and also the pi1 is made by the platelets. So platelets are involved in 2 different ways there. So in at least 3 different ways, the presence of glycine in adequate quantities prevents major adverse cardiac events. Nobody's selling drugs here. It's just one of the things that a nutrient does. And all of these conditions really are, in many ways, glycine deficiency conditions, I believe.
Yeah, and you call it the alpha and the omega of inflammation too.
Oh, of inflammation. Oh, yeah. Well, yes. Well,
yeah.
Okay. Well, I talked about the glycine-gated chloride channels on the macrophages. That has to do with the initiation of inflammation. But inflammation it's like a military response where it's, there's constantly upping the ante in terms of the strength of the reaction. So it's like like where they talk about war, where they say this is an escalation. So you have an escalating response when inflammation is actually triggered. Sometimes it really needs to be, because some infections are really nasty, like anthrax and Ebola and stuff like that. Your body really needs to do inflammation to deal with them, or those infections will kill you. Because like even the plague, bubonic plague is another one. I mean, bubonic plague I think killed more than half the people in Europe in the 14th century or the 15th century. I forget which. I say that I forget because it was a long time ago, as if I was there. But even if I was there, it was still a long time ago. I probably would have forgotten. 15th century. Anyway, it didn't kill everybody. Right? That's the thing. So your innate immune system, which inflammation is the main function of. Inflammation is your innate immune system fighting off bugs that your body has never seen before they can make specific antibodies, which takes weeks before they can crank that up through vaccination or exposure to the disease. So inflammation is what saves you if there's enough of it there. And what I say that's needed, I mean, the end stage of inflammation is literally like a nuclear detonation. It's like where these immune cells, they build up all these poisons. They build up then like a big pore in the cell, which is like the barrel of a cannon. And then, these immune poisons can now diffuse out fairly freely. And then the last stage, boom, the cell literally detonates. It explodes, and it throws these immunological poisons everywhere and does damage, so that you have an escalating situation. Well, that leads to the question as to what would happen. How is it then, in any case, that you can ever have such inflammation being self-limiting, right? I mean, people die from it. They go into sepsis and septic shock in hospitals. Very high mortality rate from these things.
Yeah. Because
the inflammation is, crazy. The recent experience we have en masse is, of course, the cytokine storm with COVID, which is because the COVID virus, the spike protein, triggers inflammation, and it causes just inflammation that's out of control. Why does it get so bad that eventually it's going to kill? Not even so eventually, but very quickly, within a matter of hours, it can kill you. Why is that? Why isn't it limited? Well, the answer turns out to be glycine. Very, very interesting. Glycine was also found in the 1980s and 90s. Another group working at the University of Michigan, another fellow named Joel, brilliant scientist, Joel Weinberg, in University of Michigan. He was a kidney transplant guy. He was working on figuring out how to prevent the kidneys from deteriorating from the time they took it out of the donor and the time it went into the recipient. Right? Because kidneys very, very, very sensitive to like hypoxia and just not having enough oxygen. They deteriorate very rapidly. So that was a problem. How do you keep them from doing that? That was a big problem. Well, they found out. Guess what the answer was? Glycine. The same thing as in this cytokine storm thing. The end stage of inflammation. Number of proteins you can name, but the upshot of it is that the final stage where these big pores develop And then not only do immunological poisons diffuse out of these pores from these macrophages, but lots of water can diffuse in, because these pores are very big. So it used to be thought that what would happen is these pores would fill up with water, fill up, and then boom, and the cell would burst. Well, guess what happens if you have enough glycine around? These pores are full, water comes in, the cells swell up, and you get all these sort of blebs, blebbing out all over, bulging out, and all these bubbles sort of out from the surface, and the cell doesn't explode. Why not?
Yeah.
Because glycine is now bonding to another protein on the cell surface, not the classical glycine receptor. Doesn't work that way. It's another one called ningerin 1, which is another protein. Ningerin 1 is a protein that is on the cell surface that kind of holds it all together, kind of keeps it together so that immune cell cannot literally explode, and therefore it's, the reaction is kind of limited there. But there are cases, as I said, with serious infections where you need that final step, that final nuclear blast where the cell needs to explode, splattering its poisons all over everywhere. And so the question becomes, how does that ever become self-limiting? How does anyone ever recover from that? Well, recover from that, again, the answer is glycine. Why? Because even if you're deficient in glycine, you still have a lot of glycine there, just not enough, as we said. When that cell explodes, it's not only splattering all these immunological poisons all over the place, it's also splattering loads and loads of glycine. Why? Glycine, it turns out, as high as it needs to be in the plasma, in which all the cells in the blood are bathed, right? And as lymph in the tissues, all of the tissue cells are basically bathed in a high glycine-containing environment. Amount of glycine is much higher inside the cell. Turns out that all cells basically pump glycine in. They use metabolic energy to take glycine that's, let's say that's at 5 millimolar, let's say that's 500 micromolar. Well, inside the cell maybe 2,500 micromolar. They pump glycine in against its concentration gradient. So it takes metabolic energy to keep the concentration of glycine higher on the inside than it is on the outside. So inside of cells, glycine is much higher. So what happens when that cell goes boom, right? And all those immunological poisons get sprayed around, killing everything in sight, and hopefully the infection before it kills you. What else is being sprayed around? Glycine.
Yeah.
So the glycine is now limiting the damage, and also preventing at a certain range, keeping the infection fairly localized at a certain range. It's keeping down the initiation of inflammation because the glycine is much higher. Now, what was the greatest evidence of this? Again, the COVID epidemic, cytokine storm. That happened in people who are glycine deficient. Well, everybody got COVID. I got COVID. I didn't get vaccinated, but I got COVID. I felt rotten. I would say it was probably the worst or the second worst intestinal viral infection I've ever had. Like an intestinal flu. I had diarrhea for about a day. I had a fever for about a day. My sense of smell was gone for a couple of weeks. My sense of taste was altered. I didn't feel like eating anything. I felt really, fatigued, and needed about 12 hours a day of sleep. So I would consider I had a moderate infection. I didn't need to be bedridden or hospitalized. And importantly, no coughing, no sneezing, no wheezing, no shortness of breath, no respiratory symptoms whatsoever. I had COVID, but no respiratory symptoms. As far as I could tell, it was not a respiratory infection. Maybe I got it that way, but it didn't affect me that way. No cytokine storm. Well, I had, I was taking glycine supplements, of course, which I've been doing for years, and other friends and family, and nobody had a serious COVID infection either. A friend of mine who was about my age, in her 60s at the time, had just had lung surgery less than a year prior for air pockets in her lungs, and took her 10 months to recover from the lung surgery. And then what happens? She gets COVID. Oh my God, what did that do to her lungs? Nothing. She was fine. Had a COVID infection, not fun, but she was fine. And everybody I knew who had glycine, that was okay. And so it's, but who were the people who were most at risk? What were the comorbidities. They were age, right? Advanced age. People in their 80s and 90s succumbed really to 80s and
Mhm.
90s. Like that Japanese study I said, right? Low
Yeah.
glycine production by your body goes down. That's one comorbidity is age. Another age, diabetes, cancer,
Mm-hmm.
obesity. And it was found recently in obesity, a group at the Mayo Clinic and in also Jacksonville, Florida, the Children's Hospital there. The first author's name is Del Prado. Very interesting study where they were looking at disease markers for heart disease because they're treating obese kids. That's what they have. They have a clinic for basically obese kids, and there's an awful lot of them. And they said, gee, I wonder if we can predict heart disease among these kids by looking at biochemical markers that go along with their obesity. And guess what they found? Obesity, decreased glycine synthesis, right?
Yeah.
So, we got this, you eat the muscle meat and you don't eat the bones, so you get a double whammy there, but then on top of that, you're eating, because you're eating too much of everything, you're getting fat, now your endogenous glycine production is going down also. So you get this, there's a triple whammy or something. See, the body is not made to have glycine be non-essential. It is essential conditionally. You don't need that much, but nowadays, because we eat so much more, because we eat more of the muscle meat, and we throw the bones in the trash instead of the soup, you have all of these things combined to give you a glycine deficiency, and that, I believe, is responsible for the whole spectrum of increased risk of heart disease and cancer and diabetes and arthritis and so many other things. It's not the sole cause of these things. It won't protect you forever. I had diabetes running in my family, and I had pre-diabetes when I was in my 50s. Blood sugar was starting to go up, and I would say I was about 20 pounds overweight, about 185 pounds. Now I'm about 165 pounds, that's my right weight, that's my college weight, So my blood sugar fasting glucose was starting to creep up into what they call diabetes now, over 125. My A1C was creeping up over 6. So I figured, well, I'll just just with the right diet and taking glycine every day, I'll avoid diabetes. Well, I did avoid diabetes for about 15 years. I stayed in the sort of impaired glucose tolerance range, where my blood sugar was between 105 and 125, but it wasn't normal, it wasn't under 100. And so, well, now that I lost the weight, and then the diabetes went away, I was back to pre-diabetic levels of blood sugar, fasting blood sugar. It's very interesting, how that happens. It's a lot to do with weight. So obesity has a lot to do with diabetes, but it's not everything. So to show you how much it has to do with it, there's a really wonderful clinical trial, placebo-controlled, randomly controlled clinical trial done in Mexico City in 2008. First author's name was Cruz. So Dr. Cruz and his colleagues, I think they only had about 37 patients, but it was a very good trial. It's very hard to do a trial like that and get significant results, because if you have patients who have diabetes, and you say, well, we want to try this nutritional strategy and see if it'll help your diabetes. So why don't you get off all your medications and just try our nutritional strategy? You can't do that. That's not ethical.
Yeah.
They're
not going to
taking
get
medicine, which is keeping their blood sugar at a safe level, and you're saying, let's never mind the medicine, just try our thing. You can't do that. So you have to let them keep taking their medicine and take your stuff also. So that makes it harder to show a significant difference. But they did. They were able to show it. They gave them 15 grams a day of glycine, 5 grams 3 times a day of glycine. They tried it for 30 days or 90 days, I think it was. Unfortunately, when they published the paper, they didn't really highlight the story about glycine. They didn't highlight the story about diabetes, because they kind of buried what I think is the most important finding was the A1C, because it's a 90-day study where A1C matters. But the group of patients who were actually taking glycine, they went from, their A1C went from an average of 8.3 to an average of 6.9, which is really a great difference. And I have lots and lots and lots of customers saying the same thing. You can look at the testimonials on sweetamine.com, and you can see people talking about their A1C coming down. But it's not the whole story. And as I said, in my family, diabetes is kind of rampant, both sides of my family. It's interesting that when I look at basically a series of 6 siblings on my mother's side, my mother's mother died of a heart attack when she was 72. She had diabetes and was taking some medication for like 20 years for it. Her brother, who also had diabetes, died at the age of 73, and he was taking medication for it for a while, of course. And then her sister and her other brother lived into their 90s, and they didn't have diabetes. Even though her sister, my Aunt Mary, was obese, she was clearly overweight and was taking blood pressure medication for the last 30 years of her life. But she lived to be 97. Because she never got diabetes. Neither did my mother, and she lived to be 96. But I was tripping into diabetes, so I have to watch it because, I'm past 72 or 73 now. I'm 75. So.
Barely. But
living on borrowed time, as they say. Well, we all are, really, but
yeah, but you seem to be doing pretty well. And I want to mention too, you haven't talked about this as much, but I talked to Dr. Senef about, there's a guy named Dr. Klinghardt who has used, funny enough, around 8 grams of glycine a day to try to kick out glyphosate if it's substituting for glycine.
Yes, right.
Yeah, so that's kind of another interesting thing, that there's a theoretical advantage to flooding the body with glycine because then it will keep glyphosate potentially from that substitution.
Well, more like it to as a detox function for against modern toxins.
Can you talk about that?
It should do that. If in fact glyphosate does substitute for glycine, I know that's Dr. Senef's hypothesis, and nobody's ever really tried it. She said maybe the Monsantos of the world, maybe they've tried it, but they haven't really said anything about it, and nobody's really wanted to fund a study. If they wanted to fund a study, it'd be pretty easy to find out if that were true. And there's plenty of circumstantial evidence that glyphosate may be substituting for glycine, even if it does it to a small degree. That's all it takes really to mess things up. You get like, if you get an error rate in making proteins of 0.001% ordinarily, because there are proofreading functions in your mitochondria, your ribosomes, and all this stuff. And if that error rate goes up to 1 or 2%, and you get proteins that have, the wrong amino acid in a few places, you're just not going to function all that well, and you're going to be prone to all kinds of chronic disease and so forth. And that's what you find with people with chronic exposure to glyphosate. Now they've even taken it out of Roundup. Glyphosate is no longer in Roundup anymore. They very cleverly, kind of quietly,
remove that. Yeah, and I'm actually talking to some people about maybe eventually doing some trial like that, because yes, glycine is, all of these things, but also important for detoxification. It's important for sleep because it works in the same way.
Yes, because that very same glycine-gated chloride channel is in fact part of the connection between the nerves in your central nervous system in your brain and spinal cord.
Yeah.
And it acts as an inhibitory neurotransmitter because, as I described before, it keeps the membrane, what's called the postsynaptic membrane, hyperpolarized. So it prevents the overactivation. So it doesn't induce sleep. It doesn't make you sleepy, but a lot of people use it to allow them to relax more. In fact, health food stores have been selling glycine for decades, as supports healthy sleep.
Yeah, and I've even seen
nutritional claim, and it'll do that.
I've even seen people taking it for anxiety, and there's a newly discovered potentially a glycine depression receptor, and huge amounts, 40 grams or so, being used in conditions like schizophrenia.
Yeah, and there have been studies like that, and they're always sort of at the margins. Those are really serious conditions. I mean, there's serious abnormalities in brain function. And so this is kind of, nibbling at the margins a little bit, and you wouldn't expect it necessarily to correct those conditions. Maybe it could be preventative. If it started beforehand, they talk about that in Alzheimer's, generalized, dementia, brain damage. I'm sure that glycine has a lot to do with, or the lack of glycine has a lot to do with traumatic brain injury and chronic encephalopathies that you find, football players and boxers and hockey players and so on. I know because I've had some severe head trauma, and to me it's just a bump in the head.
Yeah.
And it heals up and then it's gone. I had a bump in the head in, let's see, how long ago was this? April. It was April of 2018. So what is that, 8 years ago? 8 years ago, I was in a situation where I had just had a 3-hour drive. I was just going to my kid's house and Philadelphia at that time. I was living in the Hudson Valley in New York, in upstate New York, and I was dehydrated. Didn't have any water on the way. I just, just drove there. And when I got there, I sat down and I had a glass of wine. So I had a glass of wine. I was dehydrated, and then I got up from the table, and I actually fainted just for a second or a half a second, but it was just enough to hit my head, to fall and hit my head, bam, right here, very hard on the hardwood edge of the kitchen table. The next thing I know, I'm on the floor. I'm on the kitchen floor looking up, and my kids are there over me. And they're trying to ask me questions, and I was all confused. I recognized who they were and everything, but then they asked me questions about sweetamine, and I said, sweetamine? What's sweetamine? That's a really good name for something. And they said, uh-oh, we better take it to the ER. If that doesn't know what sweetamine is, we better get him to the ER right away. So they called the ambulance, and they got me to the ER, and there I was, and it really hurt where I'd gotten hit on the head. And I was there, and they did all kinds of testing, but I was there for a few hours. 2 hours after it happened, the pain went away from my head injury, although for probably a week or two it was tender. If I touched it or pressed on it, it would hurt a little. And that was it, and they said, oh, you ought to follow up with a cardiologist, follow up with this, follow up with that. I said, no, thanks, I'm fine.
Yeah.
And that was that. It was really just like, the old-fashioned Western movies where the bank robber comes in and he clunks the security guard on the head with the butt of his pistol, and knocks him out. That's basically what it is,
Yeah.
And that's what happened to me, an accidental thing like that. But it didn't do no long-lasting damage. I mean, and that was 8 years ago, and I have no kind of brain injury, nothing residual from that. It's just,
and a lot of these people in the comments are telling their what they call now Dr. Brind stories where you might have an injury, but that doesn't become massively inflamed and lead to a lot of pain.
Right.
And I didn't even tell you, and so I encourage you all, if you have a Dr. Brind story, please share it in the comments. And I didn't even tell you this, but Dr. Brind.
How do they know what Dr. Brind stories are? You mean stories of their own?
Yes, yeah. No, they're
okay.
calling them in the comments Dr. Brind
right.
stories. I have my own Dr. Brind story. But I was going to tell you, I spilled hot liquid on my leg the other day while driving that I made at 200 degrees, which I will never do again. Anyway, it resulted in these
Well, you have to sue
second-degree
McDonald's,
burns.
and then you're made for life.
It's too bad that I made it myself. And
Oh,
so I
darn.
know. Yeah, so I made a drink and I was driving my son to school, spilled it. It resulted in second-degree burns, like really bad burns.
Yeah.
But the thing is, I didn't have a lot of pain. I will admit, first 30 minutes, I was like,
Yes.
wow. And then the next few, I was able to work out. And, I had it wrapped and I took good care of it. I didn't end up having to go to the doctor, and I had huge blisters. But I believe that is a Dr. Brind story because it wasn't immobilizing and I could kind of go about my life, but it was a huge bad burn. So everyone share your Dr. Brind stories if you have them. And one of his main messages is that, inflammation is not a normal response to injury, just to infection. And
Right.
so
that's what I would say is the key discovery in all of this, the
Yes.
real, scientific breakthrough, the real scientific breakthrough was as a result of that self-experimentation on myself of taking glycine 10 grams a day, not knowing what would happen, and finding that after trauma of sunburn, trauma of blunt injury from a fall onto my tailbone and so forth, I from these things where I expected, and I was absolutely certain that inflammation would follow, and it didn't.
Yeah.
It's like all of a sudden the light bulb went on in that beat up head of mine, and it said, so that's what it is, It's and then it's like, of course, why would your immune system do inflammation when it's only going to do damage to normal tissues? Because it's believed that inflammation it's a natural thing, and it's going to. And there are all kinds of theories, hypotheses as to why it happens. So there's one hypothesis you may have heard of, that if you sprain your ankle, it gets inflamed. Well, that's a natural splint.
Yeah.
It naturally keeps it stiff so that you can't injure it anymore. Hard to imagine in the evolutionary past that a caveman running away from a saber-toothed tiger and he sprains his ankle is going to be helped by having it not letting him run or hobble as fast as he can.
You're a goner at that point.
Away from the scene. So it's like there's no real reason. Now it's interesting because there are even therapies like that. For example, there's a therapy There is therapeutic modality, I think, for like Crohn's or one of those ulcerative colitis, one of those immunologically related, inflammation associated GI problems. I think it's maybe Crohn's, where you have these doctors who believe that the reason for these conditions is that with all of the vaccinations and the sterile environment that we grow up in, that our immune system is not challenged the way it was in the caveman days by all kinds of different germs and so on. And therefore our immune system is overreacting because it's not properly utilized to react to normal things, which kind of sounds reasonable, but ultimately it doesn't hold water. What they do, and when they base their treatment modality on this, is they have these worms, intestinal worms, not good intestinal parasites, right?
No.
But they have bred out these intestinal parasites. There are worms now that really are not pathological. They're just sort of harmless parasites. They'll steal some of your nutrition, but they're not going to cause any illness. Now, one of the ways that parasites are able to survive in the host body is to secrete anti-inflammatory substances. So when they feed these people have Crohn's, terrible ulcerative colitis, whatever. Eat these worms, live worms, parasitic worms. They eat the worms, and guess what? The people get better. Now they have these live parasitic infections that are really not pathological, and they're better. So they use that as proof of the theory. I say no such thing. It's not proof of the theory at all. It's just showing that if you stop the inflammation one way or the other, you're going to improve the condition, but better off to stop the inappropriate inflammation in the beginning by having enough glycine.
I love that.
Simple as that, really.
And we didn't even mention it too, but you say mast cells also have these chloride.
Yeah, they also have glycine receptors on them, and they're related. They're a very similar origin of these cells to the various immune cells. The so-called myeloid cells. They all originate in the bone marrow and so forth. And the mast cells have a lot of similarities, and I know there's mastocytosis. There's a very serious kind of condition, and it's almost like having a food allergy, and you have to go around with an EpiPen because you can go into anaphylactic shock, almost without warning, and you don't really know what set it off. If you have, I forget what it's called, mastocytosis something syndrome, where your mast cells are just on a hair trigger to get activated into, secreting histamine, and that sets off inflammation.
Mast cell activation syndrome?
Mast cell, yeah, MCAS, that's the one, mast cell activation syndrome. And I know someone who has it, and she says, she never travels. You can't. It's like you have to almost kind of live in a bubble. Always with an EpiPen and so forth. Very, very limited dietary choices and so on. And it's hard to say about whether that's a glycine deficiency condition or not. There's some evidence that glycine's involved in it, but I couldn't. There's just not enough evidence for me to say, yes, you should take glycine supplements if you have mast cell activation syndrome. I'm hesitant to do that because you could be set off by just about anything, any little additive or any little change in the composition of whatever you're taking. So
maybe try eating.
I would say anything you eat, maybe try more of that. Like if you eat meat, if you eat collagen, if you eat gelatin, have more Jell-O, have more gelatin.
Yeah.
Try ramping that up, which will ramp up your glycine, and see if that helps. In other words, if you have MCAS and you can tolerate something like Jell-O or unsweetened gelatin, have more of it.
Bone broth. Yeah.
Or bone broth. Anything
Yeah.
like that. That's the same stuff, really. It's, it's the gelatin or collagen in there. Because what happens with bone broth, you put it in the refrigerator, what happens?
It gels up?
Gels, yeah, that's what Jell-O is. So same thing. You can have it warm, you can have it cold, you can have it Jell-O, you can have it liquid. However, it's the same, basically denatured collagen that's digestible, and it has a lot of glycine in it. So if you can tolerate that, if you have MCAS, just keep having more, ramp up slowly more of what you can tolerate, and see what having more of that will do, if it will help and make you less sensitive to those things. That would really be the way to try it.
Yeah.
I would just do a free amino acid supplement on top of that.
Yeah, I think that's great. And that brought me to the thing I want to close with is like, how do we close the glycine gap? What are the many ways we can? And food is one, like you said, gelatin,
Yeah, food is one. I
collagen,
was just thinking,
bone
it would
broth.
be a great food. You don't want to jump in anything, so you want to go cold turkey. You know what I mean? A piece of cold turkey. Cold turkey broth.
Yeah, cold turkey
So,
broth, chicken skin, pork rinds, right?
yeah, I mean, I don't know how much glycine they have. More the bones than the broth. It's really, it's not. And people, when you say bone broth, people naturally think that it's the marrow. It's not the marrow. It's the actual, that
Bone.
hard part of the bone is not just rock. It's a living rock. It's part rock and part protein, and the protein part is collagen.
Yeah.
Think of it as like, it's like biological reinforced concrete. It's a good analogy of it. It's like, it's a composites. They have like, think about when they're pouring foundation for a house or a building. They'll put in a cage made of rebar, iron rods, and those will be the fibrous parts, and then they'll pour in the concrete, the bone part, the mineral part. So your bones are like that too, except the rods are not iron rods, they're collagen fibrils. So that's the protein part of bone. There's a lot of protein in bone, and that's what bone broth is for, is that when you boil that actually leaches out the collagen or the gelatin from the bones.
Yeah.
Leaches it at collagen as gelatin. And when that's denatured and when it's subject to boiling, it's called gelatin, because then it's digestible. If you just have straight collagen, it wouldn't be digestible, right?
Yeah, and for people who, so like a cup of bone broth, 2 to 3 grams, and you can cook rice in broth, you can cook
Sure.
vegetables in broth. You can also, we have bone broths that don't taste like bone broth that you can put in your
Oh
coffee.
yeah, you got your chocolate bone broth.
Chocolate, we have caramel, we have a churro coming, a strawberry and cream. It's like we're trying to bring glycine back to people who
You're
don't
trying
want
to
to.
spoil everybody. Come on, you're
We're
trying to
trying
make
to.
your customers take your nutritious food and make it taste like candy.
I know. We're
It
just meeting
does.
people where they are. I know. If you put it in your coffee, it tastes like a mocha, but there's no sugar, right?
Right, that's right, yeah.
So there's that, and then you can eat collagenous cuts. You can actually add gelatin too, or unflavored collagen to like oatmeal. You can add it to
Sure.
smoothies. You can add it to
Because
yogurt
that's tasteless.
things.
Yeah, a lot of people, they'll
Yeah.
say, not a lot of people, but a small minority, I would say, of my customers or would-be customers, they try it and they say, do you have some way to take the sweetener out of it? Because I really can't stand anything sweet. And I say, well, you know what? You should do gelatin
Yeah.
or bone broth or something, because those things have no taste.
Yeah, and that's the
But,
thing. Like, and so you can do that, and collagenous cuts too, chicken skin, fish skin.
right.
If you're a vegetarian or a vegan, you could do something like soy or nuts and seeds. These have glycine. But so that's the food-based versions. But Dr. Brind, and what I do is I drink bone broth throughout the day. I have grass-fed meats, so there's a lot of collagen in there. But Dr. Brind, you fill yours in one fill swoop. So
I like to just take a packet of my sweet amine, which has 8 grams of
yeah,
glycine in it, and I put it in a glass, and I squeeze in the juice of a whole lemon, and add the same amount or even double the amount of water, to bring it up to about, maybe 3-4 ounces, something like that. Because you don't get 3-4 ounces from one lemon, you get about one. But I
and you
bring
can
it up
do
to
it with. Oh, sorry. Go ahead.
yeah, just squeeze the juice of a lemon, a packet of sweet amine, which is 8 grams of glycine, and then bring it up to about 3 or 4 ounces, and then just stir it, chug a lug, and it's delicious. It's like lemonade because it has a very strong lemon flavor, but it doesn't have all that. It's not so unpleasantly tart. It actually tastes like having a full flavored lemon without the tartness. It's just sweet and it's good and it doesn't have any aftertaste. And so that's how I like to take it every morning, kind of one and done. And then I still have foods that are pretty rich in glycine.
What do you eat?
Yeah, I mean walnuts are a good source. Walnuts, for a long time they used to call me Professor Walnut back in the 80s,
Yeah.
90s.
Yeah.
Because walnut is like a perfect food. It's 70% fat, and the fat is a perfect blend of omega-3, omega-6, omega-9, and saturated fat. 70% fat, and then out of the other 30%, it's about 15% protein and 5% soluble fiber, 5% insoluble fiber, and then 5% everything else water, I guess. And it's everything except minerals and oil soluble vitamins. and water, everything except minerals and water soluble vitamins. If you were allowed, if there was going to be a famine and food rationing and everything like that, and you were allowed to store one food as much as you wanted, and you could have, like, say take a vitamin mineral supplement, I would take a vitamin mineral supplement, water, and walnuts. That will sustain you.
I love that. I love
Like
that.
a perfect food, you know. And if you open up a walnut, what do you see? Brains, right? My
Yeah.
parents always told me that fish, oh, we got fish again, you know. I'd be whining, you know. The kid, I don't want to have fish anymore. Fish. Well, eat your fish. It's brain food, right? This is an old wives' tale, right? Brain food. What's it rich in? Omega-3 fatty acids. What do you need omega-3 for?
Yep.
Your brain, right?
That's right.
What do you do when you crack open a walnut? What do you see? Brains, you know. I mean, there are, you know, it's not scientific, but these are just observations, and they turn out to be true. So
I love it. And I just wanted you to comment on a few other kinds of supplements. And then, so freeform glycine, like you said, really cheap. You can use it too. But you can also do the sweet amine, I forgot to say this, in tea, in coffee, on oatmeal. So there's a lot of usages for
on
that.
anything, yeah, sure.
On anything. And this one's cheaper, but you know, you'll have to dose it
Well,
yourself.
that's cheaper because it's just glycine,
Yes.
you know.
Yes.
You know, and people say, "Oh, why should I buy your product?" Well, you buy it for convenience, for taste. As I say, we make it taste a little more like sugar. Convenience, taste. You can travel with it and everything like that. You want to buy bulk glycine, you get it cheaper, sure, go for it. But then you have to measure it out yourself, and you do have to, you know, formulate it in some way, put it in something that you don't mind the taste or the aftertaste, you know. But that's up to everybody. It's glycine by any means is going to have the same effect.
What about
the reason for the expense, the reason for the increased expense is that most of the expense, as much of the expense or more of the actual raw materials is the packaging. The putting it into those little packets or the putting it into capsules
yeah.
is equal to the expense of the cost of the glycine itself. And that's why you can buy my glycine, my sweet amine is more expensive than straight glycine powder, but it's not more expensive than anybody else's glycine that's packaged into packets or capsules.
Right.
Because that's just a real expense of doing business. And you know, people say, why should I do that? Well, a lot of people make their own coffee. A lot of people go to Starbucks and Dunkin' Donuts, you know, because of convenience, taste, convenience, portability, all of that. And when you come down to it, it's not expensive. It doesn't matter if you're spending 5 times as much for something. If you spend, you know, a nickel a day on something, or you spend 25 cents a day, what's the difference? You know, it's still very cheap, you know.
Yeah.
You know, it's if you pay 1 dime a day or 10 dimes a day or something like that. And most of my customers, you know, sweet amine, it costs you about $1 a day, give or take, depending on what quantities you buy, whether you buy it on sale and all that kind of stuff. But it's and you can try it, certainly risk-free. You know, you buy a 12-day challenge, you know, 12 packets of daily sweet amine, or if you buy a box, a monthly supply of 30. You go online, you give your credit card number, you have it shipped, you get it in a couple of days. And if you don't like it at all, you just tell us you don't like it, and we'll give you your money back. You don't have to refund the box.
Amazing.
You don't have to send us an empty box or an empty packet or give us a reason. Just say you want your money back and get your money back.
Yeah.
If you buy 6 boxes or buy a case of 15 boxes and you say, well, I really don't like it, I want my money back, we'll still give you your money back, but then you got to ship us back.
And that's
what
just
you
fair.
need, you know, obviously. But so that's it. The whole point is to make people try it. I want you to try it. You can try my glycine, you can try anybody else's. So you can go to sweetamine.com and try my sweet amine, or you can buy glycine from anywhere. But if you buy something risk-free, at least you've put up the money up front, which gives you the incentive at least to try it.
Yeah.
If you just hand out stuff for free, sure, it's free, I'll take it, I'll take 10 of these, you know, and then you never use it, because if you get it for free, you don't value it. You have to at least put in your time and attention to listening to the story about it, and you know, put up the money up front, and then if you like it, you can keep it. If you don't like it, you get your money back, and you can buy more if you want, you know, whatever you want to do. It's okay. I'm not. I didn't set out in life to be a businessman anyway. The
Yeah.
purpose of the business was to get the glycine story out,
Yeah.
and that's what provided me the exposure. The business is what provided me the exposure, and then the money to do advertising and so on and so forth. Because this is it's a capitalist society, and that's the best way to get the word out, rather than just slugging it out with a bunch of academics. And then nobody would ever know about glycine.
Right.
Because I've been making a lot of noise about it. I've been, since about 2010.
Yeah. Wow.
And, so it's been a while.
And one last thing, and yeah, I highly recommend you try it. Like I said, he's got a lot of testimonials on his site. And before I take you to the last question, so this is magnesium glycinate and also Glynac. So I just want you to tell people, would these be efficient ways to fill the glycine gap, or would they fall short?
Well, magnesium glycinate, usually they say to get 300 milligrams, which they say is a daily dose of magnesium, you need to take 2 big tablets or capsules that hold about a gram each, actually, of glycine. So magnesium, what you should know about magnesium glycinate, it's not only a nice, absorbable, tolerable way to eat magnesium, it's also 86% glycine. So some of the benefits that are touted for magnesium glycinate maybe do more to the glycine than the magnesium. You need magnesium, and if you're deficient in magnesium, you're definitely going to find some improvements. The most natural way to take magnesium is to appreciate that. Magnesium is a metal, an element, that is responsible for making green plants green in exactly the same way that iron is responsible for making red meat and blood red. That's how you could recognize the magnesium content in food. So what's the best source of magnesium? The most natural source? Spinach.
Yeah.
Take your 12-ounce can of spinach, like Popeye the Sailor Man from the old days, right? What did Popeye do when there was trouble and he needed to have all his strength? He would take a 12-ounce can of magnesium, of spinach, which has that 300 milligrams of magnesium in it. Open it up and pop that can of spinach all at once, and now he'd have a whole day's worth of magnesium in his system. Then he could go punch out any bad guys he liked. So that was an interesting cartoon, because that was a way of getting kids to eat the spinach. That was, I think, consciously part of their message, and it's a good one. There's no better source of magnesium than spinach.
Yeah. And if you're going to take magnesium glycinate, you're going to have like maybe 2 grams of glycine. So it wouldn't be that 8 to 10 gram dose. But it's
so 4 times that is a lot of pills.
Yeah. And what about Glynac? Do you know about the typical sources or the amounts of glycine in
Glynac? The NAC is a lot less. It's only about a tenth. What does it say on the jar? Yeah. You have a jar of Glynac? I
do. I was just going to look at that.
Yeah, you
so
just
right now,
did you put it away? Or
yeah, it says 1,800 milligrams of glycine in 1 serving. So again, if you're doing something like this, you'd have to take 4 servings.
How much NAC is in there?
Similar, actually, 1,800 milligrams.
Oh, really? Okay.
Yeah, so this is a 1-to-1. But again, roughly 2 grams of glycine. So
you should take about 4 or 5 times as much glycine. And that much N-acetylcysteine. N-acetylcysteine, I recommend to anyone. If you take Tylenol or acetaminophen, on a regular basis for whatever aches and pains, if you still need to after you have enough glycine, make sure you take NAC with it. And if you take Glynac, that's fine. I don't know what the pricing is like. You may be spending more money than you need to, but you can probably get supplements of NAC, also cheaper, just without taking the glycine. But whatever, it's all good. These are all good supplements. You can shop around and get the best deal for what you need and what you want to spend and everything like that. But none of them, I had never purchased any Glynac, but I imagine it's not expensive either, right?
Yeah, I don't think it's that expensive. I was just trying to demonstrate it's good, but maybe not the most efficient way.
Not for just getting glycine. No, the most efficient way to get glycine is glycine.
Yeah, glycine.
Obviously,
for eating your glycine. Well, Dr. Brind, this has been amazing. Everybody, let us know if you have questions in the comments below. We were going to get to busting some glycine myths, but we're going to do that in a part 2 later. But I think this has been very comprehensive. As you can see, Dr. Brind is just interested in everybody in raising awareness around this potential deficiency
Yes,
creating rampant inflammation. And so thank you, Dr. Brind. Tell everyone one last time where they can connect with you. And if you have any final last words of wisdom, now's the time.
Oh yeah. Final wisdom. Log on. Just go to sweetamine.com. SWEETAMINE.com. There's a lot of information, not just about the product, but about the kind of stuff that we talked about. And if you call, even if you call our customer service, or email us or whatever with a question, on the comments for these podcasts, it's kind of hard to keep up with them. I know that Autumn does a great job kind of editing them down to a digestible number of them. Yeah. A lot of repeat questions and so on. And I do try to get to them as much as I can.
Yeah.
So that I can share them with you. Because you understand, I'm a retired professor. And people said to me when I retired, they say, "Oh, Dr. Brind, don't you find that you really miss teaching?" And I said, "Miss it? Are you kidding? Look what I talk to customers all day and these podcasts and so on. You never stop teaching. I'm always giving these, what is this, 2 hours straight? I only had to go 50 minutes when I do classes."
Yeah.
But it's nice. I like the relaxed, open-ended, however much time we take. As far as we get today, we get.
Yeah.
And hopefully it provides you all with information that's interesting, enjoyable to take in, and that you're better off health-wise for it. So that's all I'm trying to do.
Yeah, and thanks for listening, everyone. I know that Dr. Brind has been one of your favorites, and he has taught me so much and everyone so much, and so look forward to a part 2 where we bust all the glycine myths that have been going around. But thanks, Dr. Brind. This has been amazing.
Okay,
And
always great to be with you. Thanks again.
And Glycine Miracle, too.
Glycine Miracle. Oh, yeah, that you get on Amazon. I don't sell that on the website.
Okay.
Because I don't want to sell anything that's subject to sales tax on the website. That's a whole other kettle of fish.
Okay.
Fishbone broth or whatever it is. But if you want, you can go to Amazon and search my name, or glycine or my name, and you will find the Glycine Miracle showing up. And then
Awesome.
You can buy that. I think it's $15.95, but well worth it. I can tell you that because I wrote it.
Yeah.
And it's got all the references. In passing, I mentioned an author here and a piece of research there and a paper here and there. All of that stuff is detailed, and it's detailed such that one of the things I really don't like about scientific writing is you write a statement about something, and then there's a little footnote, number 6. Oh, let's go to reference number 6. Who's reference number 6? Or they'll just, you'll just have the name, the first author's name, and then you have to look at that, go in your alphabetical. But this way, I have the first, whenever I mention it in the text, any research that I mention, I put the first author's name in the text.
Yeah.
And that way, you go right to the bibliography, and there's an alphabetical listing by name. And I don't have thousands of references. People might be impressed. I could put thousands of references in there. And it would be kind of legitimate because they would all be tangentially related, but what for? You're not going to read thousands of references. I think there are only, maybe there's 100 or so.
Yeah.
It's the ones that, and if you wanted to, how many references are there? I don't remember.
I don't remember, but it is a manageable amount.
It's a manageable amount, and it's not in small print, it's in just as big print as the rest of the book. Yeah, so you see that, and they're separated by spaces, so you can actually, if you you see a name in the text, you can go right to the bibliography and find that name in the references very quickly. And if you get the reference, you can go on Medline and get the reference, or at least the abstract is available. In many cases, the whole text is available. And you can research it as far as you want. I give you the tools to enable you to research any aspect of this as far as you want. And you can always call our customer service. And if you need to talk to me or want to talk to me, if I'm available, I'll be happy to talk to you. Because as you can see, I'm happy to talk about this stuff all day long.
Yes, and we'll put all the links to the trials that we discussed into the description. And we have a presentation that we will be showing these slides throughout. So thank you again, Dr. Brind. Amazing. And
all
I'll
right.
see you again for
My pleasure.
Before you go, I know what a couple of you are thinking. You're doing math. How many grams am I getting? Am I even close? So don't try to calculate it in your head while also listening to Dr. Brind. I already built it for you. It's called the Glycine Cheat Sheet, and it's free. And you're going to get a 10-question checklist so you know in in 60 seconds, whether you're low, things like waking up tired but wired, achy joints, sagging skins, or being a heavy meat eater, which, plot twist, actually makes it more likely that you're deficient. The exact size of the glycine gap and what you need to do to fill that gap every single day with simple swaps that are easy to incorporate into your routine. So grab the glycine cheat sheet now before you close this tab, because future you, sleeping better and aching less will thank you.